Okay, so this video for method 3 is going to be a lot shorter because really what method 3 is it's taking this method 2 and just spinning it, kind of turning it on its head a little bit. So instead of applying this tangential torque, what you're doing is you were just applying a torque until it's rotating at a constant angular velocity. So if you did do method 3, check out the video for method 2, and then what's going to change, so watch it up until kind of the procedure is going to change a little bit. You'd say instead of doing it from rest, you would just say, oh, keep on changing the torque until you get this constant angular velocity, until you feel like it's constant, and then check it using the slow motion camera that we talked about in method 2. So the equation is going to be the same. Everything's going to be the same here. In this case, though, or well, actually, the equation is going to be a little bit different. So everything about your method is going to be pretty dang similar. So watch up to that point in 2. And then B is where we get a little bit different. So we would say in this case, oh, our net torque is equal to I times alpha if we have no angular acceleration. If we have a constant angular velocity, then we have a 0 net torque, which means that our torque applied minus our torque friction is equal to 0. So our torque applied is equal to our frictional torque. And that's really all that our equation will boil down to. But your torque applied will just be force times R. Then what really changes is in this case, this one's actually not dependent on the angular speed. So all that we have for the angular speed is, so if we answer no, how does it not depend on the assumption? So in this case, all that we're saying is the only way that we use angular speed was to see if it was a constant angular speed. So regardless of how fast we were spinning, the only thing that we care about in regards to angular speed is that it is constant. It can be constant at any rate for this method to work. Because it canceled out in our equation, it doesn't depend on our angular speed or our change in angular speed. So as long as we're constant, it doesn't really matter. So this one is not dependent on that assumption. And then briefly describe how it would change it. If no modification is necessary, state that explicitly in either case. Describe how the data could be analyzed to determine whether the frictional torque stays constant as the angular speed changes. So this one, they're going to say, oh, you'll get a point for saying a modification that has any additional trial at angular speed, or just explicitly stating that no modification is necessary. So we would have gotten a point for saying no modification is necessary. So that would be a point for us. And then for indicating how analysis of the initial or modified experiment could plausibly determine whether frictional torque is independent of angular speed. So I guess we could say perform the experiment again at different angular speeds and see if the value of torque changes, like our applied torque. So we could do it when we're really slow, or we could do it when we're moving pretty quickly. We could be torquing the edge of our disk. If we're spinning fast and we get a different value than when we're spinning slow, we know that, hey, maybe this does have a dependence on angular speed because we had to apply a different torque in order to get that constant speed again. So that should do it. So that one, again, if you chose this method, check out what I said in method 2 about how we're going to measure the torque and how we're going to measure the angular velocity. And then the rest is, I just went over it. So yeah, give that a go, and hopefully that was okay.